So let's start our session for today. Let me present my screen. So again, a quick check whether am I audible and is my presentation visible? Yeah. So welcome to the week 8 live interaction session for the course Waste to Energy Conversion. This course is offered by Professor Prasanajit Mondal from the Department of Chemical Engineering, IIT Roorkee, Uttarakhand, under the NPTEL program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati. I conduct live interaction session for this course every week, and yes, so let's start our session. And today's topic, or probably topic of interest for this week's, is energy production from algal biomass. So just as a to recollect, as we do every week, let's just discuss what has happened for the last 7 weeks once in a very brief manner before we progress for this week's content. So first we started with the analysis on the different kind of energy conversion routes from the waste material. So we discussed about the biological route, thermal route, and then the chemical route. So first we discussed on the thermal routes, where we classified the thermal conversion process for the conversion of waste to energy into three different types: gasification, pyrolysis, and incineration. And we also discussed on the fundamentals of the three different processes and what particular parameters differentiates each one of them. After that, we discussed on the fundamentals of every single routes and the different types of reactors that is particularly used in them. And after which we moved on towards the chemical conversion routes. So we discussed there. I hope everybody is able to remember those things. So um, we discussed about the conversion of, so sorry, in biological routes we discussed about the conversion of the biomass to biogas, as well as to that of the bioalcohols or biofuels like bioethanol and biobutanol through anaerobic digestion process and fermentation process. And we also discussed about the what do you say, the process for the conversion of biomass to bioalcohols. And towards last lecture, we discussed about the energy production from transestrification reaction. We discussed what is transestrification reaction, that is wherein your esters and alcohol reacts to form alkyl esters, sorry, triglycerides plus your glycerin or glycerol. So I hope everybody is able to remember that reaction what we discussed in the last class. Let me just show that. So triglycerides will react with alcohol to form fatty acids of alkyl esters plus glycerol. So this was the fundamental. So again, and then we discussed about the catalyst used in the process, the sources of the triglycerides, their methods, and all other stuffs. So this week we will be focusing on energy production from algal biomass, or you can say algae, microalgae. So these microalgae, as well as, or you can say this algal biomass, is something that is typically very different from what we have discussed in the previous sessions. They are not something like your cooking oil or the recycled grease or the bio oils that you extract from the waste seeds, like how you saw in the transestrification reaction. So if you remember, as we saw now also, the sources of triglycerides are nothing but, apart from the waste cooking oil and the what do you say, yeah, waste cooking oil and the recycled grease, you have this waste seeds from where you extract the bio oil and then upgrade that to biodiesel. So this particular process of extracting energy from the algae or microalgae is not something very similar to what we have discussed before. So, in order to extract oil, or you can say in order to extract oil from this algal biomass, we need to grow algae. So, the typical way how this algae basically is formed, or it basically gives out this what do you say, the bio oil is that this algae, in the presence of sunlight, water, as well as carbon dioxide, basically is converted to this carbohydrate metabolites and the lipids. So by so there are two advantages of using this algae, microalgae, for this energy production. So apart from energy production, there is also another one, you can say not just one, but there are many other advantages of using algae for our energy production process. So can anyone tell me what are the advantages of using algae for energy production apart from the energy production as such? Oh, sorry. Advantages of using algae. Yes. Carbon neutrality. So these algae, because since for this cultivation of the algae, it requires carbon dioxide. So that carbon dioxide is going to be removed from the atmosphere. So that reduces the carbon dioxide content, and thus makes it eco-friendly and carbon neutral. Apart from that, you have energy production. Yes. Okay, okay. So no, so that is like okay, yeah, that is also one of the reason, but that is like how it is advantageous. So okay. Apart from that, what I was expecting was that it is used for this wastewater treatment also. Yeah. So as somebody told just now, if you apart from that oil production, if you ask why algae is suitable for this bio oil production, you have lot of other advantages as somebody listed. So rapid algal growth is one. Why algae biomass, you can say. So why algae is a kind of attractive source for this energy production because of rapid algal growth. Then any other, you have a big list of factors discussing related to why algae biomass or algal biomass. Rapid algal growth. So that is, yeah. So in saline and the brackish water, the growth of algae is more. Apart from that, so this process basically uses lots of nutrients, so which sort of minimizes the eutrophication. Yeah. And you have so again so since it uses carbon dioxide from utilizes carbon dioxide from atmosphere, utilizes CO2 from atmosphere, so carbon neutrality is sort of like maintained. Then apart from that, space requirement is like not a big issue. Space requirement is yeah, it's not an issue. So then apart also, I mean, I guess we have almost covered all the factors. So diverse species of algae is available, so that makes it a suitable, an attractive source for this energy extraction process, making it suitable for extraction, for energy extraction process. Then another one particular factor is that some species of algae have higher lipid content present in them. So, if so, why is this important that some species of algae having higher lipid content is because, so as we discussed previously, this algae consumes carbon dioxide as well as this water, and in the presence of light, they try to generate lot of metabolites. So in this metabolites, the lipid is one of the component, and these lipids are only responsible for the upgradation of your biodiesel. So the bio oil that is going to come needs to be upgraded to the biodiesel. So higher the presence of the lipid content in the algae, higher is the upgradation of the bio oil to the biodiesel, which can be utilized for your practical applications or in any kind of appliances. So that is why this particular statement is important, that some species of algae have higher lipid content, so because of that the energy production or the upgradation of the biodiesel is more. So the other metabolites, as I said, that gets generated in the process like carbohydrates and other substances are predominantly also used for energy production, but the lipid content is responsible for the upgradation of the biodiesel. So this is something to important, because throughout this cultivation of the algal biomass and the energy production from this algae, we will be focusing on how to improve the lipid content so that the energy extraction process or the amount of energy that gets generated from them is enhanced. So it's important, the amount of lipid content is responsible for the upgradation of the biodiesel. So the upgradation typically depends upon the lipid content. So this is an important factor which we need to remember, because you know the entire course or entire the four sessions on this particular concept revolves around the impact of lipid content on this energy production process. So now the question, next question comes to our mind is, so you're saying algae is there and then it takes CO2 as well as this water and sunlight and stuff, and then it generates multiple other substances. Among them lipid is one. But how does this bioalgae basically generates, or how does the algae actually produces this lipids? So that is our next question. How lipids produce, oh sorry, how lipids are produced from algae? So this is our next question. So here what happens is, so as we discussed that algae takes up CO2 as well as H2O, so the typical reaction takes place, the photosynthesis reaction. I hope everybody has an understanding on that. Or let this begin. So this gives C6H12O6 plus, yeah. So this is the reaction, and here also 8 photons are used. So this algae is, what happens is, they take actually absorb this carbon dioxide as well as that of the water molecules, and then this particular reaction takes place in the chloroplast. So the chloroplast basically contains a pigment called chlorophyll, just like how it is there in the plants. So they have this chloroplast or the chlorophyll. This chlorophyll absorbs this carbon dioxide, and then the water is also absorbed, and the reaction takes place in the chloroplast, generating C6H12O6, that is your glucose, plus 6 oxygen. This glucose molecule, or the C6 sugars as we say, is reduced in the chloroplast itself. So it gets reduced to tri trialkyl glycerides, or you can say that as lipids. So this is how it gets what do you say, it gets reduced to trialkyl glycerides or lipids. So how does this happens is that it's a quite a complex process. As you can say, it has a lot of the complexity within itself. The reaction mechanism as such is too complex, because first this 6CO2 as well as that 12H2O, I mean, first the chloroplast basically absorbs this carbon dioxide, water is also absorbed. This undergoes the reaction to form the 6C6H12O6 plus 6CO2, and in between this itself, this NADPH, so called as nicotinamide adenine diphosphate, and ATP, that is your adenosine triphosphates, gets generated. And once the C6H12O6, or the glucose, or you can say 6 carbon sugars, gets generated, they are reduced to form 3 carbon sugars, and they are further they further undergo some sort of a glycolysis process to form pyruvate and then to acetyl CoA. So it's a typically a very complex process as such. So I'm just going to keep it short towards these two reactions on how does this algae capture carbon dioxide plus water and then form this glucose, and how does this glucose gets reduced to trialkyl glycerides or the lipid generation. So so as we saw previously, diverse species of algae is present, which makes it suitable for the energy extraction process. Well, that is true, because algae, as per the as per their classification, there are different types of algae that are present, and each algae has its own characteristics and may or may not be suitable for your what do you say, bio oil generation or the bio oil production. So does anyone of them who are here, does anybody remember about the different classes of algae? Sorry, there are multiple classes of algae. So different, instead of saying classes, I'll use the word phylum. So phylum actually means that it is what do you say, a group, a kingdom of that particular um, animal or plant. It basically represents for a group or a class of that particular plants or the animals. So it's a very biological term to use. So any this thing, does anyone remember the different phylums of algae? So we have something called chlorophyta. Yes. Yeah. So first one is chlorophyta, or you can say green algae, rhodophyta, or red algae. And the typically the main reason why these get I mean the red color is basically because of the presence of a chemical called phycobilins. So chlorophyta basically contains only chlorophyll and xanthophyll, but chlorophyll is the predominant constituents. Chlorophyll A and B. So as such, chlorophyll also has multiple different variations, like, or multiple different types A, B, C, and D. So out of this chlorophyta has typically this chlorophyll A and B. Rhodophyta has chlorophyll along with chlorophyll type A and D, along with this phycobilins, which is responsible for its red color. So after that we have cyanobacteria, or you can say it as blue green algae. So they are basically so they are also an algae, but then they are called as bacteria. The reason why is it because they use sunlight for their for what do you say, for their lipid production. After that you have something called as, so these eustigmatophytes have yellow green chloroplast, and after that you have phyophyta. So this is also called as brown algae, and after that you have diatomaceae. Uh, so they have chlorophyll A and C. So these are the different phylums of algae, and one of the things that we have to remember particularly is, what is required for us is we need to actually think about the lipid content present in them. So we want to choose a phylum of algae which can basically produce higher lipid content, so that it will be advantageous for us to go for this biodiesel production or get a higher biodiesel content from them. So among all, the cyanobacteria has maximum capacity for lipid production. So these are the ones that is most attractive for us or most useful for our systems, so that we can extract more amount of lipid for more amount of biodiesel to be produced. And again, it is not necessary that all the phylums of the algae that you see here will give similar type of lipid content as well as the quantity of the lipid content. So each one, since they basically come from a different type of phylum itself, so they have a different types of chlorophyll present in them, the production of the lipid content also will vary depending upon that. Again, since as I keep saying that our motive is to make sure that the lipid production should be enhanced, people are working. So this is also given in the slide. More research is required in this area so that we can try to extract more amount of lipid content from them. More research is required. Required for enhancing the lipid production. The ways could be many different ways are being explored. So some sort of a modification within the algae, or keeping this algae in different what do you say conditions, so that the lipid production can be enhanced. Now after that, we have to discuss on this various types of, so yeah, before that, so as I said, more research is required for enhancing the lipid production. So there are also ways which has been discussed on enhancing this lipid accumulation within the bioalgae. So one is the physiochemical methods, and another one is the molecular strategies. So molecular strategies are typically something like gene slicing, or more often the genetic modification techniques. In the physiochemical techniques, we have something like nutrient stress, phytohormones, and something so called as mixotropic condition. So using these kind of physiochemical methods or the molecular strategies, there are chances of enhancing the lipid production. So again, each one is if you specifically see the molecular strategies, they are very expensive strategies, because they all deal with editing the genes or doing some sort of a genetic modification, which requires state of the art tools, and are quite expensive process. Physiochemical methods are also there, but again they need to be optimized, because every time the conditions at which these algae grow is different. So depending upon that, this condition needs to be modified for enhancing this lipid production from this algae. So how are you going to actually extract? So this is the mechanism for the production of, or you can say accumulation of this lipid content within the algae. How we are going to extract out that lipid content, or how are you going to actually cultivate this microalgae, is our next question. How to cultivate? So we use different types of reactor system for cultivation of the microalgae. So the main classification is the open what do you say pond, or you can say open photo bioreactor. And second one is the closed what closed system photobioreactor. So open pond or open photobioreactors are nothing but these are also these are the bioreactor, but then they are exposed to the atmosphere. They don't have a covering which actually protects them from the atmosphere. So they are completely open to the atmosphere without any kind of barriers or yeah manual barriers. In case of the closed system photobioreactors, it is closed. So that is the main difference between this open photobioreactor or open system photobioreactor and the closed system photobioreactor is the presence of the cover. So whether it is exposed, whether that algal growth or uh, the cultivation of this microalgae happens in the presence of or happens in the intervention of the atmosphere or it is closed from the atmosphere basically remains the basis of this classification for the bioreactors for the microalgae growth. So this is closed from the atmosphere. So they are not exposed to the atmosphere. So again, in case of the closed system photobioreactors, there are different types. So can anyone name what are the different types of closed system photobioreactors? Yes, vertical tubular, horizontal tubular. So in case of the vertical tubular, the tubes that the system uses are usually placed in the vertical manner, and in case of the horizontal tubular, the tubes are actually placed as such in a horizontal manner. So the tubes are the one which basically carries out the input as well as the output. So output will be your microalgae because the cultivation of the microalgae happens, and the input will be the requirement, the nutrient requirements and other sort of materials. So then next plate, yeah, flat panel type, and another one is the plastic bag system. So in one of these cases that you see here, either in open so in these cases, what is the thing is the degassing needs to be done. The primary reason why degassing needs to be done is because what happens is when the system is undergoing the reaction or when the algal growth is happening within the reactor system, there are chances that the oxygen intervention is also possible. So we need to make sure that the oxygen mixing is prevented. So for that process, the degassing is required in this case of system. That I'll write it separately. So degassing is important. Why? Basically because what happens is as the algal growth, I mean as I repeat said just now, as the algal growth is happening, the O2, the oxygen generation through photosynthesis process is inevitable. So we need to make sure that the oxygen does not get mixed up with this process. So in order to prevent this mixing of the oxygen, they need to be removed, and for that process we do degasification. And apart from that, you also have some sort of helical and spiral systems also for this bioreactor. Spiral system photobioreactors are also available. So it's just that all of these things basically differ only based on the shape of the tubes. If it is horizontal, tubes will be placed in the horizontal manner. If it is vertical, the tubes will be in the vertical direction. If it is a helical and spiral, then the shape will be either in the helical or in the spiral way. So helical, so spiral as such, you can visualize something that is similar to the shape of the spiral binds that you see. So that what do you say? That circular bind. So that spiral type bioreactors are also available. So that will be the shape in case if it's a spiral system photobioreactors. So in case of this, so if you see this comparison, so let's say I take open photo bioreactors in one hand and closed system photo bioreactors in another hand. As per like your understanding on that, which one do you suggest will be more feasible for us, or you can say which one will be more useful for for energy production process, or which one will give, yeah, which process as such, when you take all the factors under consideration, which process, which system is the best, closed or open? And why, like? Okay. Hmm. So space requirement in case of which one is more closed or open? Hmm. So their space requirement is less. Okay. So typically speaking, there are only two places where this open and closed system reactors actually contradicts with each other. One thing is in case of this cleaning. So all the factors for the closed bioreactor is advantageous, but the problem with them is cleaning is required in case of closed bioreactors. However, in case of open bioreactors, that is not necessary, but they have a major problem of contamination risk. So that is something which it needs to be taken under consideration when we select our reactor system. So in case of open bioreactors, as I said, it remains exposed to the atmosphere. So when it remains exposed to the atmosphere, it also means that it is going to be exposing itself to the pollutants and all the other what do you say, matter that is available within the atmosphere. So contamination risk is also considerably far higher compared to that of your closed bioreactor system. So apart from speaking of that biomass yield, yes, closed bioreactor system has a higher one. So speaking of from the from all the perspective, it is, you can easily, you can tell that the closed bioreactor system is more advantageous compared to open bioreactor system. However, performance needs to be improved in both the cases. So again in so you can say apart from this closed system open type, also we have other types of photobioreactors, something like tubular, column and flat panel. So that comes under this category only. So in case of among all the three, tubular, column and flat panel, which one you can say is actually is the best? Like tubular, and the main reason why is tubular is best. So, but again, that is just one parameter, that maximum biomass yield. But also there is a higher chances of accumulation of carbon dioxide as well as oxygen within this reactor. So there is no outlet for them to actually go out to be let out in the atmosphere. So that also we need to take under consideration. So uh, if you see that table, I'm not sure whether I have all the table or no. Or no. So I don't have that clipping here. But if you see, there are multiple different parameters: biomass yield, accumulation of O2, CO2, then if I'm not wrong, cost. So there are approximately, yes. Hmm. But again, so yeah, few parameters are good for tubular, but few parameters are good for column, and few parameters are good for flat panel. So when you see from all this perspective, what you can conclude is you cannot actually exactly say which one is best. When you see from all the perspectives of all the parameters, whatever we are discussing or whatever the factors that are affecting, we cannot exactly say which one is best. The main reason is because some perform better with respect to certain parameters, whereas others perform better in other parameters. So coming to a conclusion which one is best is typically hard in this case of comparison between tubular column and flat panel type reactor systems. So that I want something to make it clear here, because yes, typically our major aim is to make sure that these biomass yield is more, but at the same time we are also we are also required to keep other things in mind, like your what do you say, your accumulation, contamination risks, and multiple other parameters also need to be kept in mind before we take a decision as which process is suitable for biomass cultivation. So this is one thing that I had to discuss. Okay, so let's move on towards some questions, because again we will be discussing more on the theoretical aspect, but again those are there in the form of questions. So yes, let's move. So let me just remove this for the time being. If I remove this, let me just increase the slide content. Yes. Hmm. So this is, I guess it will be fine. Which of the following is not an example of saturated fatty acid? Capric acid, lauric acid, linoleic acid, and none of the above. So they are asking which of the following is not a saturated fatty acid. So I hope everybody has an understanding of what saturated fatty acids are. Or is somebody who has any confusions regarding the saturated, unsaturated terms? Yeah, double or anything more than a single bond, double, triple. But if it is saturated, then throughout the structure, they will have only single bonded carbon atoms. Linoleic acid. Okay. So that's the reason. Okay. Yes. Okay. I do not know. Let's check the table. That's the reason I have given the table here. So capric acid is a saturated acid and lauric acid is also a saturated acid, whereas linoleic acid is an unsaturated fatty acids. So this is the table. Please, I think you may be required to remember this table, I believe. So yes, so what are the different types of saturated fatty acids and what are the different types of unsaturated fatty acids? This is the entire list, I guess. This is the entire list that is available in the course. So in saturated fatty acid, you have capric acid, lauric acid, myristic acid, palmitic acid, stearic acid, archaic acid, behinic acid, and lignoceric acid. And in case of unsaturated fatty acids, you have, again, the names are typically very similar. If you see 14 is to 0 and 14 is to 1. Myrstolic acid and 16 is to 1 is palmitoleic acid. And you have saponic acid, hexadodecadinoic, hexadecatrinoic, oleic, linoleic, and alpha linoleic. Lin- Linoleic, yeah. So these are the types of fatty acids in algal cells. So it's just to make sure that people are prepared for this type of questions. I think there is a similar type of question even in the assignment, if I am not wrong. Okay, so yeah. Next, which is used as a chemical flocculant to harvest algae? Ammonium chloride, calcium chloride, ferric chloride, and none of the above. Has anybody answered? What could be the answer for the second question? Which one of the following is used as a chemical flocculant to harvest algae? Okay, ferric chloride. Any other response from anyone? First of all, what is a chemical flocculant, or what is a flocculant as such? What is a flocculant? Okay. Okay. So if I ask, so you said chemical flocculants are nothing but it's something that kind of, what do you say, enhances flocculation, something to do with flocculation. Just a second. Uh, Amit Kaushik sir, can you just, I mean, if you have anything to say, then you can. If you don't have anything to say, then you can actually mute your mic. Yeah, yeah. So that's not an issue. So yeah. So what is so flocculant? Somebody just rightly said it's something that helps in the flocculation process. Flocculant as such. So what is flocculation? We will use a separate slide. So flocculence helps in flocculation and form some sort of uh, colloids, I guess. Forms flock or flakes. So now, what is this term flocculation as such? Where colloids come out. Yes, so that's okay. Colloids comes out of suspension. So as such, the definition of flocculation is this. So you basically have a suspension, and then it's somehow either automatically, spontaneously, or by adding some sort of a agent. A colloid basically, when it comes out of the suspension in the form of flocks or flakes, you call that process as flocculation. And if you use some sort of an agent for this process to happen, then you call it as a then you call that particular agent as a flocculant. So in case of this microalgae part, flocculation is nothing but you basically add some flocculant, or by itself it basically tends to form aggregates of microalgae so that it can actually settle down at the bottom. So from microalgae perspective, this method to aggregate microalgae in the form of flocks, and to separate them from the suspension, you can say. So as I said, if you require a agent, then that particular agent is called flocculants, and in this case we basically use a flocculant so that this aggregation process is enhanced, it is promoted. So there are two types of what do you say, chemical flocculants, or two different chemicals are used as flocculants. So one is the ferric chloride, Apart from that, something called alum. How many has anyone heard about this word alum? Yeah, some sort of double salt mixture. So it basically has two salts. So the typical formula goes like this. You can write it as, I will write for potash alum or sodium alum, soda alum. So potash alum is K2SO4 dot Al2 SO4 thrice dot 24 H2O. So this is something like called potash alum, and if you replace that potassium with sodium, you have soda alum, and if you have chromium, it is called chrome alum, and so many different varieties are available. So these two are the flocculants that are used in case of this microalgae process, so that they typically settle down at the, so that they typically form flocks or aggregates, and then they can be separated from the suspension. Now in this flocculation itself, there are two different varieties of you can say types of flocculation. One is the perkinetic flocculation, and another one is the orthokinetic. Apart from that, you have another one. So totally you have three. You have something called autoflocculation. So perkinetic flocculation, any idea on what is that? So it all here, the basics depend up, the basis of flocculation depends upon the kind of motion that the particle exhibits, or yeah, you can say like that. So in case of perkinetic, it is typically governed by Brownian motion, and in case of the orthokinetic, you have the bulk motion caused by stirring of the fluid, and you have something called autoflocculation. Anyone, any idea of what is autoflocculation? Hmm. Microalgae flocculates on its own, uh, sorry, on its own, by or because of interruption of CO2 supply. So these are the three types of flocculation, and the basics of flocculation is nothing. So these flocculants, as such, what it has is they are positively charged particle. Like you said, ferric chloride, so FeCl3, so Fe3 plus. So what these do is these positively charged particle enter into the system, and then the suspension also has some particles which are of oppositively charged. So we select the flocculants in such a way that they are typically of opposite, that they are typically oppositively charged in nature. So when you add these two oppositively charged species into the system, or when you add a oppositively charged species into a system, what happens is these charged species, let's say here positive, these positively charged species enter into the system and then screens the electrostatic repulsions between the negatively charged particle that is existing. So when you take a system, you have some particles and then they are having certain charge within them. And because of the similar type of the charges, they repel each other. So once you add this positively charged particle, what happens is these positively charged particles screens the electrostatic repulsions among them and then bring all of them together, and once their size, and then they start forming aggregates, so their size starts to becoming big. Once this aggregation keeps on happening, at the end, when the size or when the dimensions become bigger and bigger than a particular limit, so in that case what happens is it cannot, the buoyancy force cannot, so in that case what happens is the gravitational force becomes greater compared to the buoyancy force, so the particles tend to settle down at the bottom. This is the fundamental concept of flocculation. So the size keeps getting bigger. Once the size becomes bigger than a particular threshold, what happens is in that case the buoyancy force cannot keep them within the liquid as suspensions, or like in the phase, in the dispersed phase. So the gravitational force will be greater. Because of that, the particle will actually settle down at the bottom. So this is one way, flocculation is one way. Apart from that, you have other multiple ways also for kind of harvesting your microalgae. The next method is something called sedimentation. Again, here also it is the gravitational force which governs this microalgae to settle down at the bottom from where it is harvested. After sedimentation, you have centrifugation. So it's centrifugation, nothing but it typically uses the centrifugal force. So because of the centrifugal force, what happens is these particles will settle down at the bottom, and the rest of the material can be separated and this algae can be harvested out. This is a commercial and an industrially utilize industrial what do you say, or you can say this is used for commercial and industrial purpose. However, there is one certain limitation for this. It is expensive because you need to require big centrifugation system. So because of that process, it's expensive, and moreover, because of the centrifugal force, the damage to the cells is also very common. Damage to cells is possible or is prevalent. So once you do this harvesting, this is the initial stage of this microalgae harvesting. And after this harvesting, you need to actually concentrate this microalgae. So for that, we typically use, I guess, sorry. So sedimentation, centrifugation, all is itself is one of the process. So you have something called flotation in the initial stage. So any idea on what is flotation? Sorry, I missed flotation before. Flotation. Yeah. Simple, you put the algae into a medium, the algae in such a way that the density of the algae is less than that particular medium. Once it starts floating, you just remove that algae from the surface. So after this initial harvesting process, you have to concentrate this microalgae. That means do more steps so that the number of the microalgae becomes more, or like you get more algae in that harvesting process. For that you do this concentration, wherein first you do is this centrifugation, and after that you do something so called as ultrasonic agitation. So it's simple. You use ultrasonic waves to agitate the system, so that because of the high energy this ultrasonic waves produces, the cells gets concentrated, or more number of the cells gets can be concentrated from this method, due to the high energy of the ultrasonic waves. More cells can be concentrated through this method. So this is one of the main techniques for harvesting the, what do you say, the microalgae. So among this all the systems of sedimentation and flocculation and flotation, that is the initial stages, the inorganic chemical flocculation method is the best because of the higher yield it generates in this process. So yeah, so the answer for this is ferric chloride. Next one is, which of the following are catalyzed transestrification process? Homogeneous base catalyzed, enzyme catalyzed. Sorry, this should be heterogeneous. Heterogeneous. Oh, sorry, it should be homogeneous. I didn't see its base and acid. So homogeneous base catalyzed, homogeneous acid catalyzed, enzyme catalyzed, and D, all of the above. I think this will be easy. Every option says catalyzed, all of the above. Uh, I mean, why did you say? Can you please come back, sir? Like, why did you say it is homogeneous base catalyzed is the answer and not all of the above? Okay. So, but again, we also discussed this in the last class itself, that it can also be acidic. So base is, yes, that is one of the reason, but then by using base what happens is there is also a lot of possibility for the formation of soap. So to avoid soap formation we do go for other kind of you know catalyst in this transestrification process. So as such transestrification process has homogeneous base, which is nothing but your NaOH and KOH, and homogeneous acid is hydrochloric acid or H2SO4, and enzyme catalyst is, just a second, it's a complex name, yes, lipozyme IM60, and okay, oh yeah, fine, and then another one is novozyme 435, if I'm not wrong. So these are all the types of catalysts that you can use in the transesterification process. Yes, basic, homogeneous basic is often utilized, but the problem is it also has one of its own limitation, that it has the possibility to form soap. So if soap is formed in the mixture, then it will reduce the efficiency of the process. I guess we discussed about what are the limitations if soap forms within the system. It will degrade the quality of the fuel and affects the properties of the fuel. So in that case, we can go for this acid catalyzed transesterification and enzyme catalyzed transesterification process. So option is D. So we have one question. So here we you just need to answer me. There are no options actually. Given three different routes for transesterification reaction, as we just discussed, base catalyst, acid catalyzed, and enzyme catalyzed, comment on the rate of reaction. Which one has a greater rate of reaction and which one has the lowest? And explain. Okay, and which one, I mean, after base catalyzed, and then enzyme. So base catalyzed has more, what do you say, has a higher rate of reaction compared to acid compared to enzyme. Am I right, sir? So the thing is, yes, it is given as such as uh, which one is greater, but is there any specific reason why base catalyst is more compared to acid compared to enzyme? Or at least let's leave enzyme catalyzed aside. Why is base catalyzed transesterification reaction has a higher or rate compared to acid catalyzed rate of reaction? Order is right. It first one is base, then comes I'll just put it here. So base catalyze is greater compared to acid catalyzed compared to enzyme catalyzed. But the question is, how, or you can say explain why such things, why is it, why is this in this particular order? So yeah. Hmm. Hmm. Mm, 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 mm. Okay, so any other response apart from this? So your this thing is, since this methanol is also a base and it is also participating as one of the component in the reaction, that is the reason it has a higher rate. Is that right, sir? Okay. So let's think about this. I mean, we have tomorrow also one more session from 5 to 7. So let's, if let me just keep this as a question for time being. We have few more questions like this also that are left out in the previous session. So let's discuss this tomorrow. The thing is, it is, we let us have I would suggest to everyone to have a look at the reaction mechanism that is given in the course, and then we can try, try to interpret from that context. So let's keep that question for tomorrow. Now, next question is, oxidation of bio oil takes place due to saturation in the fatty acid, unsaturation, both A and B, and none of the above. Unsaturation. So the reason is because since unsaturation has a double bond, the possibility of the oxygen going in attacking the double bond to form other kind of oxidized product is more, whereas in case of saturated compound, that possibility is not there. So because of that, oxidation of bio oil takes place due to the unsaturation present in the material. Next question is, which of the following is a natural antioxidant for increasing the stability of the biodiesel? So stability as such is basically because there are totally three different types of stability: oxidation stability, thermal stability, and storage stability. Biodiesel as such, when you have, they are susceptible to oxygen and other kind of interventions from the atmosphere. So because of that, their properties degrade over the period of time. So to let that not happen, we need to take some precautionary measures from our side. So one of the ways to prevent this oxidation from taking place, we can add some sort of an oxidant. So there are two different varieties of oxidant. One is the chemical, and another one is your natural oxidant, or you can say chemical or synthetic oxidant. So here I am asking, which one is a natural oxidant? Tocopherol. What about pyrogallal and propyl gallate? So these are synthetic, and yeah, these are synthetic. This is also synthetic. This is tocopherol is natural. So apart from tocopherol, what other antioxidants, natural antioxidants are can be used? Vitamin E. Hmm. And in synthetic, apart from these two, you have other compounds also, like let me just write them: butylated hydroxyanisole, hydroxyanisole, And the next one is tetra butyl hydroquinone. Hydroquinone. So, yeah, natural antioxidant is tocopherol. Next, identify the most appropriate option to explain the major challenges for microalgae. This is a easy one. It's a straightforward one. All of the above, because reactor needs to be efficient, cost efficient, and then the oil production process design should be cost efficient, and after that it is the type of microalgae, as we discussed previously also, it should have the ability to generate a higher lipid content. So that kind of particular variety is also an important challenge for this microalgae, or it's a challenge for the production of this bio oil from this microalgae. Okay, so you have another two questions. Identify the following photobioreactor. What kind of a photobioreactor you see in this particular figure? Flat panel. Again, this system classification depends upon the way the panel or the tubes is arranged. So in case of the tubular, horizontal tubular, the tubes are placed in the horizontal direction. In case of the vertical, you have the vertical columns. So here it's a flat plate. So that's what is this classification is about. After that, we have one more question. It's also a what do you say, kind of an open-ended question. Comment, you have homogeneous versus heterogeneous catalyst. You need to tell, according to you, which process would be the best for the generation of biodiesel from algae. First of all, before discussing that, whatever we discussed right now here, are these homogeneous or heterogeneous? I think I've given anyway. So these are homogeneous: NaOH, KOH, HCl, H2SO4. Since they are homogeneous in their since they are homogeneous throughout their medium, so you can call them as homogeneous base catalyst. Any example for heterogeneous catalyzed transestrification reaction? I mean, any example for heterogeneous catalyst used in this transestrification reaction? Calcium oxide supported in Al2O3. So let me just write that. CaO supported Al2O3. Then anything else? Magnesium oxide supported Al2O3. And anything more? Magnesium, zirconium, yeah, zirconium solid base catalyst. So this is one thing. But apart from that, the question is, which process, according to you, could be the best for the generation of biodiesel production? Hmm. Hmm. Homogeneous catalyst process. Hmm. So, can we list out the parameters? So, one is the conversion rate. Next one is the post treatment step processing methodology. Okay. Presence of free fatty acids, catalyst reuse, cost. So, discussing with respect to these parameters, if you see, conversion rate is high for homogeneous compared to heterogeneous, right? Heterogeneous has moderate conversions. Hetero has moderate conversions. But whereas homogeneous has high conversions. Yeah, high and fast and high. Okay. Then from post treatment steps. Okay, so that's a big limitation. Catalyst cannot be recovered in homogeneous, whereas in case of heterogeneous, catalyst can be recovered. Okay. Processing methodology limited. Okay. And in case of heterogeneous, continuous. So here limited, or you can say batch, like over there for homogeneous, and continuous in case of heterogeneous. Presence of FFA, free fatty acid, does it affect in case of homogeneous? It does affect, right? In case of homogeneous. But whereas the same thing in case of heterogeneous, it does not affect. And since catalyst cannot be recovered, so reuse is also not a is not possible in case of homogeneous, whereas it is possible in case of heterogeneous, where you can recover the catalyst, treat the catalyst back, and then use it again. Cost wise, since the catalyst from the catalyst point of view itself, if you say, since it is not, we are unable to recover the catalyst, so which means that the catalyst is gone, so the amount of money that is invested on that catalyst is also gone. So if it is an expensive catalyst, then it will incur us a lot of amount, but so from the cost as perspective also, homogeneous is much greater compared to heterogeneous. So even though the conversion rate for heterogeneous catalyzed reaction is more, however, all the other parameters go against sorry, even though the conversion rate for heterogeneous reaction is less, all the other parameters basically supports this process, in contrast to the homogeneous, where all the other parameters are against, despite them having fast and high conversion. So according to us, we can say, or according to the understanding that we have got now, we can tell that heterogeneous catalyzed transestrification process could be more suitable for generation of biodiesel from the algae. So from all factors, keeping in mind all factors discussed above, heterogeneous catalyze transesterification processes best for biodiesel generation. So this is about the theoretical, I mean the theory-based questions that we have. So let's go on towards solving some questions. We have approximately 20 more minutes left with us. Yes. I am not sure about the exact figure actually. So the question is straightforward. So bio oil extracted from an oil seed sample. So this question is not about the one that we are discussing right now. This question comes from the transestrification process that we discussed in the previous class. So the bio oil extracted from a soil seed sample has 80 percentage triglyceride containing three long chains which can produce methyl esters of lauric acid, then myristic acid and palmitic acid in equal molar ratio. Yes. So I have given the list here. So, I mean, this list is exactly, I have taken it from your course content. So, you can just, yes, which one? I mean, is it not there in this list? No, I get, but just for this thing, is this the assignment question which you are asking me right now? So, see that I have told previously also, I think in this 2 weeks before, I am by what do you say rules from the NPTEL, we are not supposed to tell the answers to any of the course the people who have registered for the course before the assignment submission deadline. So again, see, that question is a very direct question. I have given the what do you say, the list of the acid and their categories, so you can find out yourself. So I mean, I'm sorry, I cannot do much from my side in this. So this is the question. So calculate the I mean, so where, yeah, in equal molar ratio using methanol and sodium hydroxide catalyst. Calculate the amount of biodiesel produced by the transesterification of 20 kgs of bio oil. Assume the efficiency of conversion is 90 percentage and 10 percentage of palmitic acid to soap. Calculate the glycerol produced and soap formed. I mean, any, I guess it's a straightforward question I have taken. So, how to proceed with solving this? So, first we will calculate the molecular weight for all the methyl esters of lauric acid, myristic acid, and palmitic acid. This is first one for lauric acid. Then you have myristic acid. So since it is methyl ester, so we write it as CH3. Then you have palmitic acid. So what is the molecular weight? Let me use my personal calculator. So this one is 214 gram per mole. This one will be 242 gram per mole, and this one will be 270 gram per mole. I hope these are correct. Okay. So now your so this is the so the triglycerides are containing three long chains which can produce methyl esters of so and so in equal ratio during the transestrification using methanol and NaOH as a catalyst. So it will produce this trialkyl esters of this fatty acid plus glycerol. So that is the typical reaction. Triglycerides plus alcohol gives alkyl esters of free fatty acid. I write fatty acid plus glycerol. So glycerol is CH2OH, CHOH, CH2OH. So that will be, I'll write it together. So, oh sorry, OH thrice. So the molecular weight is how much? 92. Okay. 92 gram per mole. So this is the individual molecular weight of the methyl esters, but when you write it in terms of this of the triglycerides, then oh, okay. So what will be the molecular weight of the triglycerides? So how, I mean, how do we write this triglyceride molecular formula? So it will be something like this: CH2. You can write COO, CH3. It will be C11H23. So this will come from the first one for the lauric acid, and this one will be your CHCOO C13H27. We don't have space. C15H31. So this molecular weight will be 722 gram per mole. Is that fine? 722. So here our basis is going to be 20 kg of bio oil, because we are taking 20 kg bio oil is going to be our basis. So basis is 20 kg of bio oil. Now the triglyceride content is going to be, the question says 80 percentage, so which will be nothing but zero point 0.8 times of 20. So that will be 8 twos are 16. 16 kg. So in terms of moles of triglycerides, then it will be 16 by 722 grams. So here it is in kg. So you can write it as 0.722. Or you can take it as 16,000 by 722. 22.16. No, okay. 16 moles. Or you can write it as 0.02216 kilomole. So the glycerin content is, how much is the glycerin content? Assume that the efficiency of the conversion is 90 percentage. So sorry, this will be 0.02216. Let me keep it in grams everything. So 22.16 times your glycerol or this thing is 92 gram per mole. So 2038.78 78 grams, or you can write it as 2.038 kg of glycerin. Now after that we need to basically calculate what will be the mass of our biodiesel. So which will be nothing but all the moles times their molecular weight. So for the first one, that is your lauric acid ester, it will be 214 times 22.16, and for this myristic acid ester it will be 242 times 22.16, and for palmitic acid says that it has a conversion of around 90 percentage. So that means you need to incorporate that also. So it will be 270 times 22.16 times zero point 0.9. Is this fine? And these are esters. Or you can say methyl esters. Sorry. Let me put that word. Methyl esters of lauric acid. So whatever you get here will be so the total of these will be the mass of your biodiesel. Here we are asked to calculate the glycerol that will be produced, so that we have calculated already. So this much glycerol, and we have also calculated the mass of the biodiesel, which will be the sum of all the three. And we need to find how to calculate the amount of soap. So anyone? Hmm. So that's all. Yeah. So 270 times so 270 times 22.16 times zero point 0.1, because it is given that soap efficiency at which this palmitic acid is going to be converted to soap is 10 percentage only. So the mass of this palmitic so the mass of the methyl esters of the palmitic acid that is going to get converted to this bio diesel is only 0.9 percentage, and 0.1 percentage of it is going to convert it to soap. So you just multiply that. So what will be the total mass of biodiesel and soap here? So it's 27 times 22.16. 598.32 grams. So grams, like that for everything we need to calculate. So let's calculate that. 22.16 time 214, 4742.24. 24 grams, then 242 times 22.16. Sorry. So 242 times 22.16, 5362.72. And this one will be 270 times 22.16 times point 0.9, 5384.88. So if you add all this thing, you will get the mass of biodiesel. So mass of biodiesel will be 4742.24 plus 5362.72 plus 5384.88 grams. So what is the value for this addition? Mm. Grams, or you can say this as 15.489 kgs of biodiesel. So this is the calculation for the mass of the biodiesel. So if you see this triglyceride. So basics. So by taking 20 kg of bio oil as a basis, we are able to get the mass of biodiesel as 15.489 kgs. So last we have one small question. I think we can stop with not with this one. This one we can take it in the next class. This one. 100 kg of waste cooking oil was fully dissolved in some amount of neutralized ethanol by heating and titrated with N by 10 KOH solution using phenolphthalein indicator. Titer value is 120 ml. Determine the acid value of the bio oil. What is the, I mean, how to calculate acid value? Yes, yes. Concentration into volume divided by mass of the cooking oil or mass of the oil, whatever we are taking. So, what is the significance of calculating the acid value of the oil? Like, why do we calculate acid value? So, it is basically to determine the conversion of free fatty acids. Like, for example, your iodine value is to measure the degree of unsaturation in the oil. Like that, acid value is basically to determine the percentage of conversion of free fatty acid. As such, you will not use the acid value. You will take acid value at the initial condition and acid value at a particular instant of time, and then from there you will calculate the conversion of free fatty acid. So let's finish off this calculation. Very simple one. And 56.1 is actually for the molecular weight of KOH. So concentration here is it's given N by 10. So 1 molar by 10. So that is 0.1 molar times volume. Volume is given as 120 ml. The entire thing divided by 100 gram of waste. So what will be the answer? I guess it will be 1.6 point. Let me just check. 6.732. Does it has any units? It's unitless because concentration will be normal. So normality will be something in what do you say? Normality does not have any units, right? It's a dimensionless quantity. So yes, so that's all for today. Like we have two more, but oh, we had this. Okay. So we had two more questions, but this we will take up in the tomorrow's session. So tomorrow's session will be a extra live interaction session where we will try to summarize what we have learned in all the lectures together and sum it up before you go for the exam. I guess it's on 22nd March. So let me stop sharing. So any doubts or anything that you want to share? So, yes. So like I am exactly not sure about the pattern, but you can expect something, like as far as I know, you can expect something as similar to what you are doing in your assignments. It will be having a more or less, it will be having a similar pattern, just like how your assignments are. Yeah. So yes. So shall I conclude the session for today, or anything else that so okay then. So thank you for everyone who joined for today's session. I hope you will join tomorrow's session, which is scheduled from 5 to 7 p.m. As I said, it's an extra live interaction session, like a summary session. So I thank Professor Prasanajit Mondal as well as the NPTEL team for providing me this opportunity to interact with you all this Sunday afternoon. So let's meet tomorrow for our final live interaction session. And yeah, thank you. Have a happy Sunday and bye. Yeah.